All right, everybody. Well, welcome to our last session. And we'll start with Kartik Sarkar speaking about Fermi bubbles perspective from a supernova-driven wind scenario.
Thank you. So let me first start with thanking the scientific organizing committee for giving me this opportunity to speak in front of such an audience. So I'll in this talk speak about the Fermi bubbles, and I will present you some models that we did with Biman Nath and Pratik Sharma here, and it will be mostly a perspective from a supernova-driven wind scenario towards the Fermi bubbles. Okay. Thanks to Uri and Roland in the morning, I really can skip it over. But I will mention a few things. So this is the Skamare sky. These are the Fermi bubbles. This is the loop one. This is the ROSAT 67 map, which is an X-ray, and you see some shell kind of thing here, but you don't see anything here. Just to flash out a few things. And inside there is a little less amount of X-ray than we see in the shell. There is also WMF haze, which is coming from inside the Fermi bubble. Right, so these are the Fermi bubble. This is called the loop one. This is called the North Polar Spur, or I will mostly refer to as NPS. Right. We also see some polarized radiation towards the Fermi bubble. Roland pointed out that this is related to the Fermi bubbles, but Yuri says no. Okay, so we have to wait for that. Right. We also saw from Ramon's talk this week that there are some warm clumps towards the Fermi bubbles, which have from minus 200 kilometers per second to plus 200 kilometers per second velocity. I mean, within this velocity range. Right. So, many of the things that I'll be talking in this talk is that are related to the assumption that this feature NPS is really at the galactic center distance. Okay, so I want to focus a few minutes on this. And now, NPS has been the origin of the NPS has been discussed over half a century now. And it is still being discussed and debated, and in my opinion, it is getting settled down now with very recent results, and we'll see about that. So, historically, there have been two kind of arguments for the NPS. One is that it is a close by shell, which is just a 200 parsec away from the sun, and so it has a roughly 200 parsec size. The another is which is purely theoretical till now, which has been purely theoretical, is situated at 8.5 kiloparsec away at the galactic center and is of the similar size, like 8 to 10 kiloparsec in radius. Right. In my opinion, the galactic center origin scenario seems to be more plausible because of the following reasons. I mean, there are arguments for and against both of these scenarios. But in my opinion, this galactic center origin really is very strong. And why I say that is because of the following reasons. So this map shows a ROSAT R4, R5, R6 map, and this is the base of the North Polar Spur. So the North Polar Spur actually extends like this. Okay, and if you can see, there are small circles along this red box. And these are the excellent Newton pointings, okay, to obtain the spectra towards the North Polar Spur. And once they are obtained spectra, you need some column density to feed the spectra to get the spectra properly. And the obtained column density is plotted here. Okay, so these are colors represents different latitude. Okay. Interestingly, if you look at the stars towards this pointings, which was known, distance is known, so also spectra is we have very good spectra, and so extinction is known. can invert this extinction into a distance. And we always find that till 4 kiloparsec, the NH required hydrogen column density to match the spectra is always falling short. So the distance inverted column density, the extinction inverted column density always falls short of almost in every case. You can see 1 to 1. This indicates that probably this feature, this X-ray emission is coming from beyond 4 kiloparsec. Okay. And even with the error, still you will see that there is always a systematic increase, systematic higher requirement for explaining the excess spectra from the non-polar. Right. So I will assume that this NPS, I'm not assuming, but there's sufficient evidence that it is at the galactic, towards the galactic center. Right. So let's then look at some of our previous work, which works which have been done with Biman and Pratik here. So yes. Right. So yes, exactly. But if you look at the latitude here, like 6, 7, 8, 9, 10, right? If you just plot the distance, right? So at 4 kiloparsec in galactic, and if you just plot the multiply it by the angle, it would give you roughly 500 parsec. That means you are already traveling out of the disk and going through the CGM, so you would not expect any extinction from that. So that's the theoretical perspective, if the disk actually extends only to 300 parsec. So, yeah.
Physical size is also too big.
The physical size you cannot say, so it depends on the distance.
If it is 5 or 8 you see,
yeah. Yeah, even in that case it is quite big. Right. So what we do is do some simulations about hydrodynamical simulations. I should make it clear at the beginning. So what is shown here on the left panel is density distribution, and the right panel shows the temperature distribution. Okay. And the x-axis is basically the galactic plane distance, and the y-axis is the height. So this is a slice perpendicular to the galactic disk and passing through the galactic center. Okay, and we have a dense and warm galactic disk which is rotating in stellar potential, and also a steady circumgalactic medium which has lower density and higher temperature. Okay, so what we do now is we inject the supernova mechanical energy within 100 parsec of this center, and 100 parsec is basically where you see the star formation such kind of star formation going on at the center. So let me first play the movie just to show the simulation, then you can distance. Okay. Right. So you can see this, the bubble blows out in the circumgalactic medium, and then it goes out. Okay. Right. I just wanted to point out a few things in this simulation, is that if you notice very early time, so the time should be here, yes. Early time, it is still inside the disk, and it has swept up enough an interstellar medium, okay? But when it goes out of the disk, it just this swept up interstellar medium cools at the contact discontinuity because of relative and thermal instability there. Okay, but it still hangs out there because it is on the co-moving space, co-moving flow of the background hot gas. Okay, and as we proceed, we see that this gas is some of this gas will flow back. Some of this coal gas, this identity, warm clumps are moving out. Okay. So, right, and I'll come back to this cloud kinematics in later slide to compare with the Raman seeds. Right. Okay. So this is the forward shock, as you know. Then this is the contact discontinuity. We have reverse shock. We have another reverse shock, and this is where the energy injection is going on. Okay. Alright. So this is the model that we propose. So what is happening is that cosmic ray electrons are being injected here. Now this is a proposed high energy model. Okay, there is not. I mean, it seems plausible, but the cosmic ray electrons are not actually present in the simulation. So the cosmic ray electrons are being injected here. Then they get advected upwards. Then again reaccelerated at the reverse shock. Then again advected outwards. Then again gets reaccelerated in the reverse shock, and then in this turbulence. And it may happen that this whole CGM t equals to 0 contains a magnetic field, and because of this motion of the bubble upwards, it gathers some magnetic fields, and that magnetic field is actually restricting the diffusion of cosmic ray further out. I mean, this is still just an assumption, okay? I mean, we have to really do a cosmic ray simulation to see that whether it is true or not. In that case, all the cosmic ray electrons would be inside this contact discontinuity, and so that would represent the Fermi bubble. Okay? So we should look at a time when this contact discontinuity reaches 50 degrees from the solar location, right? And that, in this case, happens at 27 million years. Okay, interesting. So, right. So the corresponding energy that we see here is belongs to roughly 0.3 to 0.5 solar mass per year. Although this is not very certain because of some of the conversions that I use. Okay. Right. Since I really don't want to talk about the gamma ray modeling of the gamma ray, X-ray, radio spectrum morphology because that will take too much time. I just want to flash a few things about the cloud kinematics, since many people in this audience have worked and keep interest in cloud kinematics. So these are some defined velocity channels plotted over here, and the color shows the column density. Okay, less than for the gas, less than 4 times 10 to the 4 Kelvin. For higher energy cutoff, the calculation is still going on. Okay, so what we see is that we don't see much gas here at minus 200 to 150 kilometers per second. But as we proceed from minus 100 to 50, we see some gas. Then as we go on, there's some clouds still we see. Okay, so yes, this is the line of sight velocity from the sun. This is the line of sight velocity from the sun, considering all the effects of rotation of the solar sun itself. So this is what should be now. If this simulation was comparable, then this is what should be observed in the line emission. I mean absorption features too. So although we don't find many line of sights having line of sight velocity from minus 200 to 150, but we get some till 100. So I think I don't know what will happen if I increase the temperature threshold. Okay, but I'm still happy that I still get some of the negative velocity clouds. This is simply the column density of this gas. It has not been corrected for any neutral hydrogen column density. No, nothing yet. Yes. Please.
And so this is not the full halo parameter space, though, right? But how hard would it be for you to?
So this is where you see also the Fermi bubbles. This is the size of the Fermi.
But what if you wanted to expand to a place like where I look, where it's not the Fermi bubbles, but I would want to see
yeah, but you don't see. So you can see that outside Fermi bubble there is not much cloud.
If you let your simulation run longer, would there?
Yeah, then it will go out. But then I have to also fix my time, when is the time for the Fermi bubble. So in this case, it is 27 million years, and all these snapshots are taken at 27 million years.
You're not also modeling all the cold gas everywhere throughout the disk.
No, disk is cut off. Plus, I have not shown the zero velocity or close by velocity.
Doesn't have a realistic ISM.
No. But the realistic ISM is not visible in the in this velocity map anyway. Okay, thank you. Sorry. Yeah. So. Yeah. So this is 10 to the power 17, 10 to the power 19 centimeter square. So sorry, this is just the exponent.
Just NTR among the
Right. So if you see some of these clumps have actually close to 10 to the 1 19. Some of this red means 10 to the 1 19. Okay, so I don't say this is exact match to match what Ramon and Luke says, but I'm still happy to get some of the components. Okay, so right, not only the such like modeling, high energy modeling, we can also get some constraints from oxygen 8 to oxygen 7 line ratio, and we did that, and so we ran some simulations with varying stock motion rate for the and also varying AG and wind activity strain, and these are the different. So the top panel shows the map for the oxygen AG driven case, and the bottom panel shows for the stock motion driven case. And in almost all cases, you see, you see that as I increase the energy from left to right, the line ratio intensity ratio actually increases. And one good way to compare it with the observation is to look at the histogram of the observed intensity ratio. This is the oxygen 8 to oxygen 7 intensity ratio. It's emissivity.
Is put in.
Emissivity.
Okay.
Emissivity. Yes.
Not just constant, not just number of atoms.
No, it's the emissivity. Emissivity. Okay. Yes. N squared times the emissivity.
Yeah.
Right. So the way what you see in observation is kind of it peaks around 0.5 and then drops after 0.7. Right. So if we are comparing, then the histogram should match like this. And what we see in stock motion driven case, this is the stock motion driven case, that the best match is for 7 to 40 Earths per second, and in AGN driven case, wind driven case, the best match is at 10 to 41 Okay, so in no case we find that the energy is more than 10 to 41 Earths per second. Because, for example, if we consider a case where the AGN wind luminosity is 10 to 42 Earths per second, you always see this is represented by the blue boxes here. You always see many lines of size with line ratio more than 0.8 or 1, which is like just the opposite of this. Thank you. Yes.
What is the difference between the base band and quadrant and the stuff?
Right. So the difference is that the AGN wind is much less mass loaded and higher velocity. That's all. No, the power is presented by this. Power is presented by individual. So I vary the power.
So what would be the comparison case for an AGN of
0 Earths? Right, so that is represented by this blue. So I have cut it, so there is nothing. No, actually it is less than 0.2. Less than 0.2. So like I have intentionally cut this axis from 0.2.
You need some process.
Yes, you need some process to edge it up. Right, so the last point, and I will just wrap it up very quickly. This one question still remains puzzling, is that if the shell, the X-ray shell, was actually the substrate of circumgalactic medium, that should have been present in the southern hemisphere too, right? But we don't see any southern polar spur in the X-ray or even southern loop 1 in the gamma ray. Okay, so what can be the answer? Now, came up with some solution, but it's still under investigation. I will not depend much on it, but still, this is a solution that can explain this. So what we do, this simulation is same, except that the southern hemisphere has 20% less CGM density. Yes, CGM density, and this could happen because of the asymmetric gram pressure that the Milky Way gets when it is moving through the intra-group medium. Okay, but well, I agree that this is not quite justified yet. But let's see what this assumption leads us to. So these are some density snapshots, and at different times. As you can see, the forward shock in the southern hemisphere moves faster than the northern one, and at this time, when the northern one reaches 50 degrees, the southern bubble reaches 57 degrees. Okay? That means there is a asymmetry in the size of the Fermi bubbles too that we should have observed. And do we see that do we see that in observation? I think yes. So this is what I plotted is this. Right. So what I plotted here is both the bubbles, Fermi bubbles in one canvas. So the magenta lines show the northern one, and the green line shows the southern one. And it appears that the southern one is at like roughly 4 to 5 degrees bigger than the northern one, except this push from this left side. So I think this is still consistent that and it is encouraging that the southern one is actually bigger. And this is the X-ray synthetic X-ray map, sky map, and we see that we actually get this X-ray cavity kind of stuff where the Fermi bubble is, which is represented by this loop. And we also see some loop 1 feature in the northern hemisphere, like a shock, but we don't see anything in the southern hemisphere, not much signature. And why does that happen? It happens because of 2 reasons. First, a 20% decrease in the circumgalactic medium density gives you a reduction of 40 in the X-ray emissivity by 40%, okay, roughly. And the second thing is that, since if you can notice, we are roughly here at 8.5 kiloparsec, and the southern shock has just crossed us. So we are inside the shock, and in projection effect, we don't see, we lose the ability to detect the shock in the southern hemisphere because we are inside. This is purely provided by the projection effects. Alright, and just for sake of comparison, this you can see this is the observed fluorescent map, and this is the obtained map. In the gamma ray, I will also see in gamma ray we see that just again painting the some kind of high energy physics. Don't worry about it much. So we see that the permeables are almost good shape. We of course don't include any cosmic diffusion. And also we see a northern loop 1 feature in the northern side. Okay, and this can be seen also in the observation here if you see northern loop 1 side. But in the southern hemisphere, just there are like 2 horns coming out here and there in the low map, but there is no large scale structure. Okay. Then does that mean that this is inconsistent? I would say no. Because the power law that I have taken, power law of the electron spectrum that I have taken to get the cosmic ray, gamma ray intensity, roughly 2.4, and that is because of the shock acceleration. Now remember, in the southern hemisphere, we are already inside the shock. So what we would see is a little steeper cosmic ray electron spectrum. So if we put that just from 2.4 to 2.45 in the southern hemisphere, this decreases by a factor of 2. I mean, there is 50% reduction, and it gets completely indistinguishable with the background. Okay, so I think this is the end. Okay, can summarize that the since this model, the size, shape, X-ray, gamma ray, radiation. Of course, this emission I have not discussed much, but I am happy to discuss after the talk. Is consistent. UV absorption is quite kind of encouraging, but of course we need to do some more work to see why you don't get much less velocity, much negative velocity. Using the star function at the center, the age of the bubble seems to be 30 million years roughly, and which is consistent with the synchrotron cooling of the cosmic electron that just Roland pointed out in this morning, and of course UV is right. So oxygen 87 line also supports the energetics of this model, and the asymmetry of the NPS, the loop 1, are achievable in the southern hemisphere if we decrease the circumgalactic medium density by only 20%, and this is still like point of debate. But since that these 3 features like NPS, loop 1, and NPS may have a common origin at the galactic center and may be forming a nuclear triad. That's it. Thank you. Before you ask questions, the limitations.
I was going to ask about that image that I flashed up from the Lockman and Kluger's paper of the extraplanar H1.
Yes.
Have you thought about trying to model that? Whether you could, because it's the region of where the extraplanar H1 is sort of cleared out above this goes out to the back of the polyspheric. So.
If you see there is a clearance the central part. So this would really be consistent with the central H1 that you see. Okay. And we also see some clouds that are coming off from the center. This is very transient phenomenon. So you can like, it is no surprise that, I will not be surprised if you find some clouds here. Variation clouds, okay, some that some. Yes.
So, to make the assumption, how will it be seen observation?
Right, very good question. I myself have been thinking about that. So one thing is that really we can look at the oxygen 8 and 7 lines, intensity, north versus south. And just to flash out some interesting thing that we see some, I did this estimation with Fermi, and you see that, the northern one seems to be a little bit higher intensity than the southern hemisphere, just excluding the central Fermi shock, what we see. And the difference is sufficiently more than the area of 8. Okay? So there's a real difference between the northern and southern hemisphere. But again, the area estimation in these cases are very, very tough and complex, so I will not go into that much about this.
I think that it is very complex if you look at emission. When assumption line studies are very robust, and that's what I wrote down for myself. Check the difference in north and south. So
yes.
Yeah, that we can easily do.
Yeah, I don't remember whether he was looking at the absorption or the emission plans of such. Good point, I should ask him.
Just comment this question. This means the difference in masses in the north part and in the south part, that of the 9 solar masses. The difference in the ISM.
CGM. CGM?
No, CGM and ISM.
Okay.
Because this effect comes from the ISM.
This is a CGM effect. I'm reducing the density of the CGM, not the ISM by 20%. So the CGM, the ISM is still kept equal in both hemispheres.
So I think just to sort of complete that, what I think he's implying is, how do you get such a mass disparity between north and south?
So that's what I said, it doesn't have to extend all the way to 200 kiloparsec. It can extend till 15 kiloparsec only, and that could happen because of some asymmetric gravitation plus previous stop motion activity. Again, I'm not betting my life on it. Okay, it's just a fun part, and the fun part turns out to be very good, exciting. That's all.
So, yeah, so you have an age of about 27 megayears to make a Fermi bubble.
Yes.
Roland was telling us it takes about 100 million years.
Right.
So can you comment on the difference?
Yes, I guess this Roland's model is analytical model, and there's the kind of limit that you can achieve in analytical model. Is that in analytical model you have to drive the whole shell out. Okay. And so to reach there, you need more and more power or more energy, more time. Whereas in asymmetric model like this, if you blow bubble like in conical wind, you don't have to kind of sweep up all the matter. Just make a channel out and just a fraction of the matter. I guess that's the main difference that brings with the 2D assessment. Yes, please.
But also notice the sublimation.
Yeah, that's what I was.
Yeah. So yes. Okay. I should comment on that. Right. So the request transformation rate seems to be 0.5 solar mass. Thank you for pointing it out. But the observed is 0.1 solar mass per year. But the point is, I have directly converted this from the mechanical luminosity, and this conversion is not trivial, as we have seen from ED talk as well as Siddhartha's talk about the cosmic pressure, magnetic pressure, and also the higher efficiency of thermalization. So this rate can actually come down because if you improve such effects. Okay, so this is a simple naive conversion from the mechanical luminosity to stop motion.
Okay, well, I'm afraid we must move on now. Thank you very much.